of you, and thank you for joining us for the second edition of Smarter Conversations, a thought leadership series by AMNS India, proudly presented by Magdalis. At AMNS India, we believe that conversations can spark ideas, inspire innovation, and build a better tomorrow. Smarter Conversations brings together visionary voices and pioneering minds to explore insights that build and ideas that inspire. Today, we turn our focus to a truly transformative topic: the agrivoltaic opportunity, resilience, revenue, and renewable power. Agrivoltaic sits at the intersection of agriculture and solar energy, offering solutions to two of our greatest challenges: food security and clean energy. And we are excited to deep dive into this, one of the most foremost experts in the field. It is our pleasure to introduce our distinguished speaker, Mr. Vivek Saraf, founder and CEO of Sunseed APV Private Limited, a pioneering expert in agrivoltaics with 25 years of experience in finance and renewable energy. He is known for blending finance, innovation, and sustainability to address the food, water, energy nexus. Mr. Saraf is a global thought leader, having shared his insights on international platforms to shape the future of farming and energy, and alumnus of IIT Kanpur and Thunderbird School of Global Management. He is driving research-led progress in this sector. We are thrilled to have him join us today to share his perspective on building resilience, unlocking revenue, and scaling renewable power through agrivoltaics. Let me hand it over to Mr. Vivek Saraf to begin this conversation. Over to you, sir.
Thank you so much, Meet, for the generous introduction. Good evening, everybody. As Meet mentioned, I'm Vivek Saraf, the founder and CEO of Sunseed APV. We're a startup focused on agrivoltaics. I would like to thank AMNS India for giving me the opportunity to speak in the second edition of Smarter Conversations. So I'm sure you will have a lot of questions as we go through. So you can type your questions in the questions box and we will take them at the end. And in case we don't have enough time at the end, you can send it over email as well, and I will address them later on. So Sunseed we call ourselves India's first agrivoltaics technology company. Just because agrivoltaics is still nascent and some of you may not be aware, it's the co-location of solar generation and crop cultivation on the same piece of land. Some of the pictures you see here are from our research farms that we have, both of them in the state of Maharashtra. And we will talk more about agrivoltaics. But just to start, for one of these projects, we had made a video, and we'll play that video right now.
The rapid development of large-scale solar projects has become one of the major societal successes of our time. However, future adoption could be limited by shortage of suitable land as solar generation starts to compete with food production. To help resolve this conflict, Sunseed and Keynote Energy, in partnership with GIZ and in collaboration with local farmers, have set up an agrivoltaics facility where solar generation is co-located with crop cultivation on the same piece of land. This 1.4 megawatts agrivoltaics farm on 5 acres of land is part of a bigger solar project located in the Marathwada region of Maharashtra in western India. The highlight of the project is the 1.5-acre, 4 meters elevated system integrated with a shade net house growing trellising vegetables, capsicum, cherry tomatoes, cucumbers, and beetle leaves, and shade-loving flowers, roses, hibiscus, chrysanthemums, and tuberose. All these crops are also being grown in an open area as a control environment. The innovative mounting structure uses Sunseed's tensioned cable systems, having the same robust design concepts as in suspension bridges. The easy-to-install and lightweight system is about 25% less expensive than conventional structures. The structures also incorporate several features that enable advanced agriculture: mechanisms for retractable shade nets, trellises for crop support, and foggers for temperature control. The shade nets can be retracted in just a few minutes based on the radiation intensity and temperature profile, which are monitored via weather stations to provide the optimal growing environment. In addition to the shade house, systems with lower elevations of 1.25 meters and 1.75 meters have also been installed, which incur only marginally higher capital costs than conventional solar projects. These sections will be growing turmeric, marigolds, melons, leafy greens, and Ayurvedic herbs. Initially, the land at the site was hard, clayey, lumpy, and full of weeds, making it tough to prepare the land below the panels. Many tractors with different farm implements were used to prepare the soil and create granular beds ready for cultivation. Apart from helping enhance crop yields, the shade house is designed to increase power generation as well. The higher albedo of the system due to the highly reflective shade nets and mulches, along with the higher elevation and greater distance between rows of panels, is expected to double the bifacial gain. Separately, the cooling of the panels due to the evapotranspiration is expected to increase panel efficiency during the dry months. In a water-stressed region, it was imperative to have an efficient irrigation strategy. Water is being pumped from a well via a solar pump that connects to a drip irrigation network, which is triggered based on soil moisture sensors installed in each crop section. The reduced evapotranspiration due to the shade is expected to result in additional savings of 30 to 40%. Rainwater will be harvested via a drainage network aided by trenches below panel edges and gradation of the land such that the water flows to the natural drains at the periphery where it gets stored via a check dam. The solar panels are being cleaned via automatic cleaning robots, which are shifted from one row to another via an elevated walkway and supplemented by occasional water cleaning. The project is set up with IoT-based instrumentation to enable extensive R&D. This includes development of photosynthesis response curves and measurement of temperature profiles for simulating crops yields, and accurate bifacial gain analysis using spectroradiometers and albedometers. The research will help develop crop-specific technologies to create commercially viable and bankable projects. Agrivoltaics can have a profound impact creating integrated, sustainable, and climate-resilient food-water energy systems. Agrivoltaics can increase crop and energy yields while reducing the use of land and water, helping form a win-win partnership between solar developers and farmers. Come, join us in this journey as we discover new facets of the fascinating world of agrivoltaics.
So, yeah, thanks for watching the video, and we'll be back to the presentation. And although in the video, there's a lot of information that was there, but we'll probably go through some of it again. And because we want to be very clear on why we're doing it. So we're going to address why agrivoltaics, what's the purpose? So the case for agrivoltaics is essentially that you have an increasing population in the world, so more food is needed, and you have more and more extreme climate events happening, which is reducing your crop productivity. And at the same time, you have solar projects coming in and taking land away from cultivation. So clearly the trend is unsustainable, and especially in countries where land is a bit scarce. So that's where agrivoltaics comes in, which is agriculture plus photovoltaics, and you get a fancy term called agrivoltaics. Now, how does this help? So obviously now you have this dual use of farmland where you're both generating food and energy. Then the shade also gives climate resilience to the crop, and especially in hot climates like India and Africa, Middle East, everywhere where the temperatures are very high. So you have this whole aspect of climate resilience to the crop. We lose productivity because of heat, and this can help if done in the right way. This can help with that. Then you have a lot of savings on water. Agriculture uses 80% of India's water. So any savings there, 20, 30, 40% different scenarios is very welcome. And then there's obviously, because a farmer is going to be a stakeholder in the project, so not probably a owner, but a stakeholder, and there will be an increase in his income. So there's social impact that can happen through this as well. So just quickly to let you know what's happening globally in agrivoltaics. So Europe has been leading the way. They've done a lot of good research, a lot of pilots over the last 10 years, Germany, France, Italy, Spain, and now all these countries have agrivoltaic specific policies which incentivize agrivoltaics, and they're looking at a deployment of around 10 gigawatt in the next 4 or 5 years. The US is a bit behind. The research is happening right now. Some states, individual states do have incentives, and they're getting there as well. Japan and Korea have been doing agrivoltaics for quite a while, about 2 decades, but they haven't really scaled much. The policies have not been very supportive. So there's small projects happening. So a lot of projects, but smaller in size. It hasn't really scaled that much. China has apparently done gigawatts. We see some pictures, really innovative stuff, but no one really has the details. India, we have a lot of pilots that have been installed recently, and there's 20, 30 pilots that are out there. There's a couple of commercial projects out there as well. Policy incentives are being considered right now and probably, hopefully, will be in place by early next year. Awareness has been skyrocketing. So you can see that the second webinar in this series is on agrivoltaics. So awareness is surely happening a lot. And again, the Middle East, Africa, very much, not much happening yet, but very much like India, huge potential. Now, agrivoltaics can be done in a lot of different ways. So the key is that you're elevating your panels and you have crops growing underneath. Now you could elevate up to 5-6 meters, or you could elevate just a bit, and there are different cropping strategies, different designs. So I'll walk you through some of what we have experimented in our farms. So there's 2 separate research farms, but then they combine to have 4 or 5 different designs under which we have been experimenting and doing a lot of technical research on different crops. So what you see in these pictures right here is one of the projects in Parbhani, where the elevation is not too much. It's just 1.75. So the ground clearance is 1.75 meter. In a normal fixed tilt project, you would have 0.5 meter. So the additional cost of doing this is small, but then you can't really do agriculture on all of it. Some of the land area, which is always under darkness below the panels, it's tough to grow even crops that require less amount of light. You can grow them, but the yields are not really successful. But then there's a lot of agriculture you can do in the interspace between the rows and in different seasons, even below the panels or in some portion below the panels in different seasons based on the light profile during those months. So here in this, we have done a bunch of different crops. So you can see marigolds and cabbage. Here, marigolds did well. The cabbage below the panels didn't do too well. We've tried out wheat, soya bean, pigeon pea as well. And in general, if we look at the full area below and between the panels, there has been a yield penalty in this particular section. So the additional project costs here are limited, like if we compare with the conventional system, 5 to 7%, but then cultivation is limited as well. Now, the one that the video also focused more on is the shade house. So this is a 4-meter elevation system at the same place. So you can see here in this picture, this is just when we had planted the saplings. So you see all these mulches and all these saplings on it. And then you see a shade net that's retracted. And these panels are all, the ground clearance is 4 meters. So in this same one, now in this picture, you see the shade net is drawn. And this is our first, one of the first crops of cucumbers. They did really well. And you can see the growth here. And then these are pictures, cherry tomatoes, even bananas. So bananas, you have these dwarf varieties that grow only up to about 3 meters. So we tried that as well. And all of these, so banana was like kind of neutral, cherry tomatoes, cucumbers, we had higher yields than you would have in the open field. So here the ground coverage ratio was about 40%. The additional project cost was about 25 to 30% because now you're elevating to 4 meters, so that costs a lot. And then there was some of this agriculture infrastructure out there, like the nets, the foggers, so all of that combined, this was the project cost. And we've tried a bunch of different crops, the ones you see on the screen, turmeric, ginger, a lot of different flowers. And most of these, we got yields close to 100% or higher. This has been a successful model. One of the key things here worth highlighting is the generation. So the solar generation, and these are all bifacial panels here. So the solar generation, the bifacial gain has been quite high. So we have achieved a 9 to 10% bifacial gain, which is 5 to 6% higher than the bifacial gain in a 1.25 meter elevation system at the same site. So we had a control for the solar, and just comparing that, there was a 5 to 6% additional gain, which is very significant. So good project IRR, and there's another slide on financials, so I'll skip that for the moment. Now this is not our project, but popular way of doing agrivoltaics. So I thought I'll cover this. It's called vertical bifacial. So you have these bifacial, and these are high bifaciality panels that they generally use. So they're facing east and west. And these are popular because there's no synergies here because the panels are separate and the cropping is essentially separate. But then the advantage is that all these crops that require a lot of light, you can do agrivoltaics with that. So there's certain business cases where this works well, although there's a loss in generation. So if I compare it with the ground mount bifacial, there's a 8 to 10% less generation. The cost is still higher. But then there are use cases for staple crops. So all those macronutrients and this stuff that you do at scale, so wheat, rice, oilseeds, cotton, all of this can be done in this way. And one advantage why it's happening a lot in Europe is the generation curve. So the blue line is a typical solar generation from morning to evening. But then the red line shows what happens with this vertical bifacial. So you get these two bumps in morning and evening. So in a lot of countries where that coincides with the peak power consumption, and if you have a time of day tariff, then the economics get a bit different. So that's one use case. Now this is another of our projects in Nasik at Sahyadri Farms. So this is our second research project, and here we have a single axis tracker at 4 meters. And the crops we are growing here are citrus trees and grapes, and Sahyadri is a grape exporter, so that's the primary test here. So this you can see, so we haven't had our first harvest yet, so it's going to be the first grapes are going to come this November. There's a 1.5 year lead time, and the first harvest will happen early next year, but the grape plants are growing and they're doing well. So here again, the additional project costs, again when we say additional, we're comparing with ground mounted bifacial project without trackers. So here it's about 35%, but then again you have the whole tracking gain on the solar side, plus all the benefits of the higher bifacial gain as well. So this is one of the, in terms of project returns, this design in our opinion is something that works quite well. And one of the advantages of using trackers is that you can develop, so right now trackers are maximizing solar radiation. But now when you have revenue from crops and solar generation, then you want to maximize the combination of that. So what we are doing is developing algorithms, crop-specific algorithms for the tracking that will ensure that the crop gets the most amount of light during critical growing phases, like when they're fruiting, and at the same time, not sacrificing too much of the solar. So this way you have a dynamic movement that can help your crop growth even better. Then we have a couple of projects that are coming up that I'd like to highlight, because just that you know what all can happen. So the project that you saw with the shade net, that I would in retrospect we say was a half-hearted attempt at climate controlled cultivation as in agrivoltaics. And from what we've learned from that, we're coming up with a very sophisticated agrivoltaics net house, which has a few layers of protection. So a insect net, and then a thermal screen, a rain protection kit. So kind of taking care of all the elements and providing an ideal growing environment. And the solar panels are an integrated part of that infrastructure. So it's not that it's just there in isolation and you're trying to navigate through it. No, what we're trying to do is that the solar is in perfect harmony with the agriculture and the agriculture infrastructure that's installed. So it's playing a function, it has a role there. So here we're talking about crop yields, or the profit or the cash flows from the crop are going to be almost equal, and eventually with time they will exceed that from the solar. So this is like really sophisticated cultivation. The project cost will be 2x of a conventional solar project, but then the revenues are in that proportion or even higher as well. So this is something that we're looking at. It's going to be on the ground in a few months, and something that we feel can be scaled up. So India needs a lot of climate control cultivation. If you look at the numbers compared to the West, we lag far behind. So all the micronutrients can be grown. So for wheat, rice, etc., open field is the best. But when you do micronutrients, so vegetables, spices, everything, then this works really well. Another thing that we're coming up with the pilot is trying to do a rooftop polyhouse with solar, obviously. And this is going to be set up at the MNRE's NICE campus. And that should be on the ground as well in a few months. So here what we're trying to do is combine urban farming with rooftop solar project. So rooftop solar obviously is very popular, and with this Pradhan Mantri Surya Ghar Yojana, it's gained much more momentum. And urban farming also started to be a thing. So we're like, why don't we try to combine these and have like good organic? So all this we're trying to do in an organic medium. So not real soil, but a cocoa peat based growing medium, and grow like these very expensive exotic salad greens, herbs, maybe flowers. And you're doing that right in the middle of the city with access to high paying consumers. There's no middlemen, no wastage of food, no transportation costs, and you can get fresh produce directly to customers through this. So this is something we believe can scale as well. At the moment, our first pilot coming up in a few months. Now, we'd like to look at some of the economics. So you saw a few different systems, and I just wanted to go through the relative differences in costs and returns, and what are the different things in which there are additional costs, what are the different revenue streams, and what are the IRRs that you can get. So this is based on our experience. So different people, other people might give you different numbers. So this is our experience, some of which is extrapolated from what we've done, because ours was a research farm. So some of our costs are higher, but we've tried to extrapolate that to see what would happen if we were to do this commercially. So again, on the left, you see we have a normal ground mount fixed tilt project. Then we're comparing a ground mount fixed tilt agri PV, which is a higher 1.75 meter elevation. Then a tracker where the center of the panel is 2.25 meter elevation, a vertical bifacial APV, which goes up 3 meters. Then a fixed tilt elevated system, 4 meters, elevated tracker at 4 meters, and then the climate controlled one that we saw, which is at a 6 meter elevation. So these are the systems we're looking to compare. And so you can see numbers, what is the land use? So we go up from 2.5 acres for a normal fixed tilt up to 3.5 acres for some of these systems, and vertical bifacial is always higher, and there's a much higher land use there. Then we're comparing the structure weight. So you can see the difference here. A normal ground mount is just around 21 metric tons per megawatt these days. These are all per megawatt numbers. And then you can see how it changes. And at 6 meters, we're talking about with a tracker, and we're talking about 90 metric tons. So that's how the cost increases. So then just adding all of this up, we come down to all the different things. So on the solar side, the steel, foundations, electronics for the tracker, installation costs, because with elevation, they change as well. And then there's some other, apart from the structure, some other costs, like you'll need to buy a tractor, some farm implements, put up a drip irrigation system. In some of these, as you saw, you could have other agri infrastructure for hydroponic cultivation. So all of this combined, if you look at it, then the difference in total capex looks like what you have in the last row at the bottom. So this is how all these different systems fare in terms of capex, and all these percentage changes are against a normal ground mount bifacial project. Now, just with the same systems, moving on from capex to then the electricity generation. So in this row, you see what is the difference in electricity generation. So we're talking the base case of, we've taken like 16 lakh units as the base case for the ground mount, and then how the others fare as compared to it. So you can see we're getting with trackers and the bifacial gain 20-21% additional generation for that. And as the vertical, you see that it's on the minus, so you're minus 7%. Now, assuming an electricity tariff of 3 rupees, which is reasonable given agrivoltaics is going to happen at a smaller scale. So you have Kusum projects. So 3 rupees is a pretty reasonable assumption. If you go into the CNI, you could actually get higher, but then there are other risks associated with that. So with these numbers, and then from our experience, adding what the agri income could be in each one of these, we've got the total operating income, and based on the capex, we've tried to get to an internal rate of return as well. So you can see here, one thing that I would like to highlight is just the enormous difference in the climate controlled cultivation on the crop income, right? So we're looking at, for a megawatt, 3.5 acres, 52 lakhs of, and this is income, this is profit on the agri side, as compared to the numbers 4, 5, 6 lakhs in other systems. So that's why that scores very well. And you see that, so if the base case IRR is 13.75%, then we're talking about slightly actually lower for a 1.75 meter. For trackers, it goes up 14.5, 13, 15%, very low for the vertical, and then at around 20% for the climate control. But obviously with the caveat that the climate control is on paper at the moment, and the system is yet to be installed. So this is just a graph. I'll skip this slide. So now if we come back to, like, the benefits. So there's a reason why we're doing agrivoltaics, and then while you start doing it, you figure that there's a lot of different benefits you could get. So obviously the land use, but then one thing that we always feel, and which is understated in Europe because it's different there, there is a lot of capital available in agriculture in Europe, but in India, agriculture has been lack of capital, and it's starved of capital, I would say. And this is a means to bring capital to agriculture. So just that aspect of it will boost productivity, because now you are able to do some good things which farmers are otherwise unable to do that. Then obviously the climate resilience that we spoke about, and in some of these systems, if you figure it out right, design it right, you could possibly shift the crop patterns as well from a seasonal perspective. So if I can change the season by a month, get off-season prices, and then at a broader level, you're shifting from, this can enable a shift from these staple crops to higher value fruits, vegetable crops, which is one of the goals of the government right now anyway, because there's just too much of staples right now, and more value add crops can be grown. Now, I'm going to quickly move on to, so far it seems like, oh, agrivoltaics is great, right? And let's look at what the problem is, and especially what's kind of one of or few of the main issues that are hindering the growth of agrivoltaics in India at the moment and other places. The first one we'll look at is on the science side, so on the technology side. So what happens in agrivoltaics is that you're blocking light from the crops, right? And that is changing. If you're blocking radiation, you're changing the light available, and you're changing the microclimate as well. So at the moment, there's not enough, or there's an absence of deeper scientific understanding regarding that, and which leads to improper cropping strategies. And because there are higher capital costs associated with agrivoltaics, which are upfront, so if you're not making the right decisions on the design or on the cropping strategies, that can lead to poor economic viability. And if you're unable to properly forecast the yields, then there's a bankability problem as well. So to understand this a bit better, I'm going to go into, like, I don't know which grade we learned all this, but photosynthesis, we all know the photosynthesis equation. So you have carbon dioxide and water being converted to glucose or carbohydrates and oxygen. Now, there are two main factors, environmental factors, that this photosynthesis of a crop depends on. One is light, and the other is the temperature. So if you look at these curves here, on the top left, you have what a typical light response curve of photosynthesis looks like. And this is different for each crop. So the shape may be similar. So you do have, initially it goes up linearly and then it flattens out. but then the slope, where it flattens out, everything is different for each crop. So you can see here that, but what does happen is that after a certain amount of light, the light can't, there's no more use of more light. So it's not that you keep getting light and you can keep getting more photosynthesis. And then similarly on the temperature, you see there's a optimal here, and then it falls off very quickly on each side. And this optimal usually is around 27-30 degrees. And this is one reason India has low crop productivity, because in daytime we get such high temperatures that photosynthesis stops. So photosynthesis stops, no more food, so then it affects the crop growth. So now what we've done on the right is just as an example, and this is based on an actual experiment we did in Raipur. So just seeing, so the black curve is for a crop in full sun for cucumber, and then the red curve is in agrivoltaics in a specific design. So you can see during the afternoon when there was actually no photosynthesis happening on the full sun, you had a lot of it still doing well on the agri PV. So the area under the curve on the red graph is higher than the black one, and that is directly proportional to the crop yield. And that's what we're trying to play on in agrivoltaics. So the combination, so get enough light, because more light is not useful, reduce the temperature, and the air temperature doesn't change, but what matters is the leaf temperature. And the leaf temperature is dependent on the air temperature and the direct heat falling on the leaf. So the direct heat becomes much less, so your photosynthesis goes up. So that's basically the science that you're trying to play on when you're doing agrivoltaics. Now, typically, just so that for you to get a broad idea, what do different types of crops need in terms of light? And the unit is moles per meter square per day. That's the typical unit for light requirements for crops. And as you can see, so all the staples, grains, pulses, they require a lot of light. Then you come down, so vegetables like tomatoes, cucumbers, 20 to 30 moles, fruits, similar, flowers a bit less, green leafy vegetables even more, and then spices are also requiring less light. So these are the crops, I would say from 3 down to 7 is what you can do in agrivoltaics. And that works very well in terms of economics as well, because now if you're paying extra money to elevate your panels, you need to make that money from the profit from the crop production over the years and from the additional solar generation as well. So now all these grains, pulses, they're low value crops. So they require more light, so not good technically and not good economically as well, because there's only so much, even if they're successful, there's so much money you can make through it. So it works well, vegetables, fruits, spices, all of these are good crops to do in agrivoltaics. Now, just to dig a bit deeper into the science, so what all is affected by the light and microclimate? So that's what we're changing. So everything else is the same, right? You're assuming you have the same agricultural practices in open field versus agrivoltaics. What's changing is the light and microclimate. When we say microclimate, then we are talking about leaf temperature, a bit air temperature. Obviously, the PAR is the light. So it's called photosynthetically active radiation. So when we talk about the full radiation, the solar spectrum, you have UV, visible light, and infrared. So PAR is that visible light. So for photosynthesis, it's only the visible light, which is PAR, is what is useful, which is around 45% of the total radiation. So that is what's important here. So the soil temperature also changes, a bit of humidity, and then the airflow also gets affected a bit. The main things are PAR and leaf temperature. The others are lesser effects, but they do play a role as well. And now, because of changes here, what kind of physiological processes in the crop growth get changed? So the one that we already spoke about was photosynthesis, and this is the most important one, because this is where you're making your food. You make less food, less yield. It's pretty simple, it's pretty linear and straightforward. But then what you're also changing here is the rate of transpiration through the stomatal conductance. The plant architecture growth can change. If your soil temperature changes, the nutrient absorption via the root could change. Then flowering or flower drops that are typical. That happens so in high temperatures, so with reduction, so you're affecting that. The maturity time of the fruit gets affected because of temperature. And then obviously, very importantly, your marketable yield changes, because in open field, you have a lot of sunburn and scalding that happens in fruiting crops. So like capsicums, tomatoes typically are crops, apples, a lot of scalding. So 20 to 30% of your yield is lost or becomes very poor quality. And this is one advantage here that you can have, is that you can prevent that, if not for 100%, but a good amount of fruits in the farm. Now, to do well commercially, to do agrivoltaics commercially, you need to have good returns, obviously, and bankability. And that's what we are trying to do, or trying to create a strategy or methodology on how you can do projects that are commercially successful. So we have a six-pronged approach, and we'll go through a bit of that. But the key again here is to lower your cost as much as possible, because that's you have additional cost. So you want to lower that additional cost as much as possible. And that's mostly possible through creating the right amount of synergies between the solar and agri. So that's where, again, it cannot be a forced marriage here. There has to be symbiosis. The solar needs to help the agriculture needs to help the solar. There need to be cost synergies, and that's the only way you can make this successful. And so you need to have a very scientific approach to this, understand the science behind things, and then develop these strategies to be able to generate projects with good returns. So for this, one of the things that we've done, and this is huge effort over the last two and a half, 3 years actually, is the development of a very deep tech simulation model that actually simulates the crop yield, the solar yield, based on any design that you do. So it's basically a decision support system, a software that is used to design your agrivoltaics project. And it's based on a lot of different scientific modules. So it has a lot of proprietary data that we've been generating at our farms, creating 3D models of crops, all the photosynthesis response curves, and then creating a lot of scientific modules, doing optical ray tracing to get the light simulation, energy balances to get the temperature simulation, and then generating the Farquhar parameters to get photosynthesis. So there's a lot of things we're doing there, and with the goal to design the right project that can be commercially viable. So what this entails is, and I'll quickly skip a few slides to come here, it helps you in your decision making for the project. So we're talking about what kind of system do you need to select. So is it a tracker, a east-west canopy, a fixed tilt, vertical? And then once you have that, then you need to figure out, should I have some transparency in the panels? What should be the dimension, the pitch, the height, azimuth, panel configuration, 1P, 2P, 1L? Should there be any gaps between the panels? So all of these answers can come through this, because you can create all these scenarios, run the simulation, and then compare how you are faring on all these, on the solar generation as well as the cumulative photosynthesis across the cycle of the crop. Then similarly on the crop side, we're talking about decisions for what crop can we have an intercropping strategy, because between 2 rows of solar, there'll be like 4 or 5 different crop beds, with each one getting different amounts of light. So based on that, you can figure, okay, I'm going to grow this crop on these 2 beds, but a different crop here, because the environment is different. Then it will help you figure out, you need to integrate some agri infrastructure, calculate the crop water requirement, and that's a big thing as well, because water, as we're all aware, is a problem already, and it's only going to increase being a problem. So if you can predict the water use well, and you're saving water because of the shade, that's a big benefit here as well. So these are some of the decisions that you make, and this is some sample output from the system. So on the top right, you see leaf temperature simulations, photosynthetic carbon assimilation on the bottom, the light distribution on the ground, on the backside of panels, and all of this is available in all different types of graphs, Excel numbers. So try to be very flexible on how these numbers can be used. So coming back here, and this slide shows, as I mentioned, about the photosynthesis response curve. See, these are the instruments that we've been using on our farms to generate those for a lot of different crops. And this is kind of at the heart of how the system calculates the photosynthesis. This is an example of a project that we did, designing a project for an apple farm in Israel. So the problem statement was they already had an apple farm, apple trees growing in a certain way, certain layout. So what is the best possible solar design that you can have for it? So these are different response curves at different temperatures. So they went through the whole process to get a recommendation. Now quickly on the policy side. Now agrivoltaics in India is, as I said earlier, very nascent, a lot of potential, but there are a lot of issues as well, because right now there is no definition of agrivoltaics. And if there's something's not defined, then it's not really bankable either, right? Because what's someone going to evaluate you on? So the first thing that you need is for the government, MNRE or different state renewable agencies to create a definition so that it provides the basis for policy formulation, and then promote business models that are viable. How does a developer work with a farmer? And then one of the main things is also the land use, because right now it's kind of vague. When you put a solar project, land use actually changes to non-agriculture or commercial, and that's a problem because then you cannot use free water, and industrial labor laws kick in. Agri income will be taxable because if it's commercial land, anything that's happening there is a commercial activity, even if it's agriculture. So there's some core issues that need to be addressed by policymakers. But the good news is that they are in the process of addressing those, and we're likely to see policy incentives and policy definitions coming in next year. Then another issue is the financing of it. Even though I've been saying that the right design, the right project with the right crops, you can actually make more money than a conventional solar. But the truth is that at the moment, you pay more capital cost upfront, and what you get is over the years. And how do you get people to believe that that's possible, or get them to do the right thing? So there is some financial incentive that's needed initially so that the gap, extra capital, some of it at least can be covered. And then if some pilots are promoted, then with 4 or 5 years of data, people will see that, oh, wow, this is working well. Gradually that subsidy can go. But that's the way we look at it, that initially to promote this, some capital subsidy is needed. All countries in Europe have it, and it's likely that India will as well. But there are other ways to help as well, right? And you can get cheaper debt via development finance institutions. And one thing that I always like to say is that, you have this whole ALMM panels in India, right, where they're more expensive. So you just remove that requirement, let Chinese panels come in at their original price, and then you have the Chinese subsidizing agrivoltaics. So we may not need to subsidize it ourselves anyways if we allow that. So I'll quickly move on. Now, you saw in the video, the McNelis video at the start, and how it's better steel, better corrosion protection than zinc only. And then there's obviously galvalume has been used a lot over the years, which is zinc plus aluminum. And here in McNelis, we have zinc, aluminum, and magnesium. And the biggest thing is that it's self-healing. So the cuts, abrasions don't harm it. And one thing that to me and for agrivoltaics, this is very important, because in agrivoltaics, you're in a higher corrosion environment. There's more water around there all the time. Then you have fertilizers, some pesticides being sprayed, and you don't know. So right now we don't know what effect it will have, but then having better corrosion protection is definitely would make you feel better. So there is clearly something that this can be useful for agrivoltaics. And the good part is because you have higher thicknesses up to 3.2 mm, so all these taller structures, hollow sections can be covered in that. So you saw the different applications in the video as well. So solar structures, greenhouses, silos, safety barriers, flooring, walls, roofing systems, all kinds of things there. This has a use apart from solar. The last thing I would like to touch upon quickly is another thing that we have done that I haven't discussed so far is our lightweight cable technology based structures. So as I repeatedly said, the higher cost comes from the higher elevation. So your cost of steel, cost of structure is what's making agrivoltaics expensive. So you want to try to reduce that extra cost as much as possible. And that's where cable structures come in. So now going back to the pictures of the project, now you'll see these cables that are going from column to column, connecting one row to another. These stabilize the top of the column, and you can have reduced size of columns with no negative effect. So these are not compromised for any wind loads or safety. And this really helps in saving. So we have been able to do these projects at 15 to 20% less structure cost because of these cable structure designs. And this is a very basic design. We did it in both the 4-meter elevation projects. And here you see the cables going here. And then this is something in the past, but just wanted, because we're talking cable structures, this is a cable truss project, 25-meter span between columns. So you see cable trusses. This is a canal project in Punjab that we had done prior to starting with agrivoltaics. This is another canal project. So cable structures are really helpful if you have longer elevations and higher structures. It really helps with the costs. And this here again, the highly corrosive environment. So something like McNellis is really beneficial as well. So I'm going to stop here. I think I've slightly gone over time because we need time for questions as well. Happy to answer questions. So I see 4 questions right now. So I will start with the question, income shown is annual income. So Himanshu Paptani is asking if, so yes, so all the income shown in any figure on the table or anywhere else was all annual. They were always on a per megawatt basis. Then a question from Zarir Mistri. The cable system of mounting the modules is your design or is it a design from an MMS vendor? It is actually our design. So we don't have any production. So this is our design and it can be manufactured, fabricated by others. The wire ropes come from your usual companies. So Usha Martin, Bharat Ropes. The assumed life of agrivoltaics plant coming from Siddharth, same as 25 years. Yes, so it's the same as 25 years. The structures are all designed using the same wind code. So it's all 25 and these days probably 30 years actually. Then another question on actual loading standard considered. So yeah, we've used the same Indian wind code. So same specifications that you would for any structure, all that has been used to design those. Another question from Siddharth is, has there been any study on the reduction of soiling on the module? So the answer is no. I mean, I can't say has there been any, we haven't done it. So the answer from us is no, we have not done such a study. There could be in Europe, people may have done this study. We also wanted to do it, but then there's just so much happening and this seemed a bit less important than some of the other stuff we wanted to do. So we left this out, but it's a very important point, but we don't know the answer. Then, because there's no other questions, okay, so some questions are coming up as I speak. Does the increased use of cropping assist in improved groundwater table levels? No. So if you're doing cropping, then you're actually using more water. So if at all, it's going to decrease your groundwater compared to if you were not doing agriculture at all. But if you're doing agriculture and then doing agriculture in agrivoltaics, you're using less water, so that way groundwater level can come up. But if you were doing just solar and no cropping, then obviously they would, on that land, less water would be consumed. So that answers that. The name of our company, it's Sunseed APV. So you have this on the bottom right here. Then I'll cover a couple of questions that where the folks have left, or because it says, but maybe they haven't. So are there government subsidies or policy incentives? So I had mentioned that they're not there in India yet, but we know a couple of states and the MNRE also, they are considering it. And as part of Kusum 2.0, which comes in next year, we are very hopeful that something's going to come out then. Then a very good question, how can agrivoltaics be introduced to small and marginal farmers who may lack capital investment capability? So this is where the whole business model comes in. So how do you do this where the project can be viable and at the same time a marginal farmer can benefit from it? So as rightly mentioned in the question, they don't really have capital investment possibilities, capabilities. So what we see and what we think is a good model is for a developer to lease the land from a marginal farmer. And then, so the marginal farmer is getting land rent. And then you employ or make that farmer a stakeholder in your farm as well, because you need people to do the agriculture. So depending on his capability, he could be the supervisor, he could be the a labor, but then he's getting a fixed income. So now from the marginal farmer having risky income, usually growing rice and wheat and cotton, where he makes 50,000 rupees per acre per year, which does not include his own labor, his family's labor costs. Now, if you give him lease rent, you give him a fixed salary, give him a variable salary based on how well the agriculture does, he can easily make 1.5 to 2 times what he was without the risk as well, right? Or he could say, okay, I've leased my land, you do what you want, I'll go to the city and take up a job. So, but either which way, his income is increasing. And ideally, you want him to stay, you want this to generate employment in villages. So people stay, they work, and they make more money. And most importantly, the risk has gone away from them. And now it's on the developer. So there's more questions coming in. This design is around 20%. Yes, so the structure with the, so the question is it 20% lesser cost than conventional design? Yes, in our estimate, based on the height, it could change. It could be 15, 20, 25, but yes, around that number. In the area between modules is also planted. How are the modules used, cleaned? Further, because of less soiling, would you need less water for cleaning? See, what we have done is we have robotic cleaning, and because the system is elevated, so we have a walkway on the east-west edge, or on one edge, you have a walkway. So like in typical ground mount projects, you don't have a robot for each row, right? So you have a robot, you put it on one row, it cleans, comes back, then you lift it, put it on the next row. So for a ground mount project, you do all that standing on the ground. Now here in agrivoltaics, you have this high elevation, so we built a walkway for that. So that replaces what you would do on the ground. There are other ways as well. In the next project, we're going to experiment with sprinklers. So high pressure sprinklers, because that project is even higher at 6 meters. So, but we don't know, there are possible issues with sprinklers. They get clogged over time. So we'll see how that goes, but that's another option.
I think there's one question. Is there any possibility to send us the design, or this is a patented design from Sunseed?
So it's not patented, but yes, I mean, we could do the design for a fee. We won't send the design, but it's not patented per se, because cable structures are there. I mean, you won't get a patented. They've been around for a while. So the application is new with solar structures, but cable technology is very old.
Sure, I think mostly we have covered all the questions. So thank you so much for this valuable session. The information that you provided us were quite helpful. I think I'll also thank the audience for listening patiently, being attentive, and asking a lot of questions as we see. So stay tuned. We'll have a new webinar soon, the next month, and we'll come up with a new topic to engage you and share more insights. Thank you, Mr. Vivek Saraf, and thank you all for joining in.
Pleasure. Thank you, everyone.